So let's talk about the rules around filling orbitals with electrons, and then this will help us write the electron configuration. So electrons are added to the lowest energy orbital available. And this goes back to Gen Chem where we talked about the stair step thing, where the first step would be the lowest energy level, and that's 1s. And after 1s gets filled, then we fill in 2s, and then 2p, and then we go up to 3s, and so on and so forth. The reason for this is because nature favors lower energy systems. So nature's lazy. It wants to be in the lowest energy, so it doesn't have to exert that much energy. So electrons are going to start off as low as they can go. If they don't have to put forth the effort to get all the way up to 3s, they won't. And so we fill up one step at a time. So thankfully there's a format that can be used to determine the lowest energy available. Alright, so we looked at this a bit during Gen Chem. We broke our periodic table into sections. Okay, when you write the electron orbital notation, you wind up with this right here being the S block, this right here being the D block, and this right here being the P block, with the only exception being helium, which is also part of the S block, even though it's over here with the noble gases. And so what this shows us then is we start with 1s, and once 1s gets filled, we come over here to the second row in the S block, and we start with 2s. After 2s is filled, we come over here. Now we're in the P block, but we're still in the second row, and so we're in the 2p. And P can hold 6 electrons, 2 per orbital, or 2 per sublevel. And then after 2p is filled, we come down here. This is row 3 now, and since it's row 3, it's 3. It's the S block, so it's S. So after 3s, then what comes next? The P. And after P, S, and then we see right here, now we enter the D block. And remember that these are scattered, so the only difference here is now we're in the 4th row, but the 4th row is 3D, and then comes 4P afterwards. So really, you don't need to memorize the stair step, you just need to have a periodic table, which you'll always have a periodic table on all tests. As long as you got that periodic table, just remember S, P, and D, and then that the D blocks are one off from the other one. So after 4s is 3d, after 5 is 4, 6, 5, 7, 6. And then this block right down here would be the F block, and remember those show up right in here. So after 6s would come 4f, after 4f would come 5d. So rather than memorizing all the way from 1s to 6d or 7p, just remember that your periodic table gives you the map. Alright, so here's how we write then electron configurations. So the large number that's in front gives us the principal quantum number. Principal quantum number is the level that it's on away from the nucleus. So the large number would just represent which row. And so basically it gives us the distance of those electrons from the nucleus. Even though they're not going in circles like that necessarily, it tells us the average radius of those electrons away from the nucleus. Then the letter tells us the orbital type, so it's an S, P, D, F. And then this right here tells us the number of electrons inside of that subshell. So S can hold 2, P can hold 6, D 10, F 14. Here it is for helium. So now helium has 2 electrons. Since S can hold 2 electrons, we would put that second electron still right there. So we would end up with 1s2. First row, S orbital, 2 electrons inside of that S orbital right there. Alright, so lithium. Lithium has 3 electrons. And if we look at our periodic table or think about it, we know that the 1s comes first, and it can hold 2 electrons. So that's 2 of the 3. After 1s would come 2s, because we're going on to that second row in the S block. And there's only 1 electron left, and so it would be 1s2, 2s1. Also, we have the noble gas notation, which the noble gas notation, helium, which is a noble gas, its electron configuration is 1s2. So kind of a shorthand for this, we can eliminate that thing that it has in common and just say helium 2s1, which means the electron configuration for lithium is the electron configuration for helium, 1s2, plus 2s1 as well. You know, when we're talking about things like lithium, it doesn't really seem like that much of a shortcut. When we get to grander elements that have a lot longer of electron configurations, this shortcut is literally a shortcut. So give beryllium a shot, write the standard notation, which is written out completely, and then write the noble gas notation as well. Then resume the video and check your answer. So there we go, 4 electrons in beryllium, so 1s2, 2s2 written out completely. Noble gas notation would be helium, 2s2. And so here's just a list of several different orbital notations, and we can see that we have it in both the standard or completely written out, and then the noble gas notation as well. And then once we get to neon, so after fluorine we get to neon, and at this point we have 8 valence electrons, so that n equals 2 is full, and so that means we can start using neon for our noble gas notation. So sodium, rather than writing 1s2, 2s2, 2p6, 3s1, we can just write neon 3s1, because that's this configuration, that are the same, they have that in common, followed by 3s1. 2 more for you to practice. These are a bit longer. Give them a shot. Use your periodic table kind of as your guide. Try not to use the stair step because that's not going to be given to you anywhere else. So unless you want to commit that thing to memory, which I wouldn't recommend, practice using your periodic table to figure out what energy level you're on. Alright, here it is for scandium. So scandium goes all the way up to the 3D level. And if we look at the configuration, the one that fills up the P, or the last one that fills up P, would be 3p6, which would be the electron configuration for argon. And so we can write argon 4s2 3d1. Alright, samarium is quite a bit longer. It goes all the way up to 4f5. But if you follow the periodic table and see how it goes, you should be able to come up with this fairly easily. And if we want to do the noble gas notation, we can follow this over and find that the last P6 is right there at the 5. And that would be the noble gas notation for xenon. And then it followed by 6s2, 4f5. Okay, let's talk about the orbital notation then. So the orbital notation, that's the one with the up and the down arrows and the different sublevels. So the rules for that, first off, the Aufbau principle, which that's German for building up. Each orbital can hold a maximum of 2 electrons that will spin in opposite directions. So 2 electrons, and that's it, and they have to spin in opposite directions. When you have more than one orbital in a subshell, so P, D, F, a single spin electron in each is added before you add any down electrons. So we go 1, 1, 1, then down, down, down. That's the Hund's rule. So here it is for lithium, and remember lithium had 3 electrons, and we knew it was 1s2, 2s1. And so we show the 2 electrons in the 1s, one's going up, one's going down, so they're spinning opposite directions. And only 2 electrons can occupy that. And then the 1 electron in the 2s. Typical practice is to draw the first arrows pointing up, but it's relative. If you draw them down, that's fine as long as you draw them all down. Right, here's fluorine. So remember, fluorine was 1s2, 2s2, 2p5. And notice how we don't have just a single 2p. So when we write out the electron configuration, we put all of the 2p's together. So there's 5 electrons in the 2p. But here we can see that we broke the 2p's apart into 3 separate sublevels. So this entire thing is the 2p orbital, but then those are the 3 different 2p sublevels. And when we talked about last section, this would be the 2px, 2py, and 2pz. Each sublevel can hold a maximum of 2 electrons, and since there's 3 sublevels in 2p, that means 2p can hold a total of 6, which we already knew. And notice how the ones that are sharing a sublevel are spinning opposite directions. That is a must. Let's write the orbital notation for nitrogen together. So we've got the electron configuration as 1s2, 2s2, 2p3, and so we would come and we can just draw it out like this real quick. Now if we go in and start adding those electrons, we can see that there's 2 in the 1s, and so we'd add our 2 electrons there, so up and down, and then in 2s there's also 2, up and then down, and now 2p3, so if we put those in, up, down, because they have to be spinning opposites, and then up. This is incorrect. So this is the Hund's rule. The Hund's rule says electrons do not like to be together if they do not have to be. Remember, electrons are all negative, which means they repel each other. So they don't want to have to occupy the same room if they don't have to. Check it out. There's an extra 2p orbital with no one occupying it. So this electron right here has no reason to shack up with that electron right there. It would be much happier with a room of its own because then they don't repel each other. You don't go back and add the next electron in until there's no more room available. They'll only share a room if they absolutely have to. But keep in mind that only applies to electrons in the same orbital. So, we wouldn't go through and just add up electrons across this entire board. 1s we'd have to fill, then 2s, and then 2p. But since 2p, they're all in the same orbital, we would go through and add them differently. So here is a correct placement for nitrogen then. We've got our 1s and our 2s are the same, but for 2p, we go up, up, up. 3 different rooms, no one has to share because there's plenty of room for all. And also notice how they're all spinning the same direction. That's likewise important. Okay, they're still nearby each other, and one of the ways they alleviate that is by all kind of spinning the same direction. Okay, so and it doesn't really matter if you go up, 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 or down, 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 as long as they're all going the same direction. But the typical practice is to draw them all up first. What this does then is creates a lower energy system. Remember, electrons are lazy, just like everyone else, and so they want to be in as low as energy as possible. And if we went beyond nitrogen, say we went up to oxygen or fluorine, we would come in and start adding those other electrons. So oxygen's next electron would go right there, and then we would have fluorine, and then last we would have neon. So we go up, 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 then down, down, down. Now that one's filled, so we would go to the 3s, and we could start filling that one. One of the things that the orbital notation shows us is what kind of elements are paramagnetic or diamagnetic. Write these words down and commit them to memory. You need to know the difference between paramagnetic and diamagnetic. So an element that is paramagnetic is one that has unpaired electrons. So if we look here at carbon, carbon has 2 unpaired electrons in its 2p orbital. Those unshared sublevels, like this guy and this guy, means that this element would be attracted to a magnetic field. Now, some elements, this does correlate to things that are magnetic. Iron, if you put iron near a magnet, it is attracted to it, and that's because iron is paramagnetic. However, carbon, you don't really think of it as magnetic. That's, pencil lead. If you put a magnet near pencil lead, it doesn't really feel like it pulls over there. Okay, and that's because it's not as magnetic as something like iron, but it is affected by a magnetic field, just on a scale that we can't see or feel at our level. So if you want to figure out if an element is paramagnetic, you would have to look at the orbital notation and see if there's any unpaired electrons. Here's a trick, though. Hopefully it doesn't mess you up down the road, but all elements that have an odd number of electrons must be paramagnetic. Once more, every element, if it has an odd number of electrons, 1, 3, 5, 7, so on and so forth, it has to be paramagnetic. There's no way you can have a pairing, so every electron matched up if you have an odd number. Someone's going to be left alone, and so it has to be paramagnetic. So all odd numbers of electrons, paramagnetic. However, not all paramagnetic atoms are odd numbered. So you can have an even number of electrons and still be paramagnetic. Hopefully that's not too confusing. But with that, we can talk about diamagnetic. So diamagnetic are ones that have an even matchup, so every single electron is paired with another electron, and so these elements would not be attracted to a magnetic field. And that's because all of the electrons, they cancel each other out, and so we would wind up with no attraction to that magnetic field. So diamagnetic atoms, there's really no way to tell if an element's diamagnetic without writing out its orbital notation. So I said that an odd number means it has to be paramagnetic. An even number does not mean that it's diamagnetic. You can have an even number of electrons and still be paramagnetic, which we saw in the last example. Carbon, 6 electrons. That's an even number, but it's still paramagnetic. So remember, paramagnetic, unpaired electrons, diamagnetic, paired electrons. Paramagnetic, attracted to a magnetic field. Diamagnetic, not affected by an electric field or a magnetic field. Do remember those words and do remember how to tell the difference.